Dear colleagues, my name is Ondřej Dvořáček. It's a pleasure for me to present the project I spoke about at the last convention in Yosemite. The project is dealing with the recording of hardwood cutting forces on the novel experimental device. I would like to introduce myself. I work as a junior researcher in a company Woodkey Plus Kompetenzzentrum holds in Tulln in Austria. I'm also a PhD student in mechanical engineering at Technical University in Graz. The project I'm working on is called HARDIS, meaning Hardwood Disintegration. Mechanical disintegration is one of the key processes in woodworking. The knowledge of forces and mechanisms taking place during it is very important for tool and machine development. Most of cutting processes are circular, for example sawing or milling. Therefore, it's much harder to describe mechanisms taking place during wood disintegration, mostly because the cuts are not in sufficient distance each other and signals are convoluted. For basic investigation, it's better to use a linear cut. The problem is that it is hard to achieve higher speeds. This device, constructed by Krenke, enables to measure with maximum speed of 7 meters per second. Within the project, we have developed a unique laboratory device. It is mainly used to measure the forces present during wood cutting. It works on the basis of a rotating arm. The arm has a diameter of 4 meters. It enables us to consider the movement of its end as linear. It rotates at speed of up to 8 revolutions per second. It is about 360 kilometers per hour. If we take a closer look at the whole construction of the whole device, it must be well secured due to its size and speed. It is protected from the outside by various systems and mechanical barriers. But the main part is inside. It is a rotating arm. This must not bend or vibrate too much at this speed and under the cutting force load. This picture describes the measurement principle. It's separated into two parts interact at the top of the knife. The left is dynamic rotor arm. In effect, it's rotation movement, but the radius is that long that we can consider it linear in the outer end. The right part includes the knife placed on the quartz force sensor. Wooden sample, in this study beechwood, is fixed to the rotor arm, and when it passes, the cut occurs. The sliding table drives this test setup to the position right before cut. The major advantage of having a static knife and a force sensor below the knife is to improve transfer behavior and to reduce vibrations caused by movement. Besides of other correction method based on transfer function, we are able to correct data according to real chip thickness. Correction is based on the detection of the sample surface before and after cut by means of a laser displacement sensor. As you can see in the picture, chip thickness accuracy may vary a lot. I will explain the data correction method on an example. We said that we want to cut chip thickness of 0.1 mm, but real values are somewhere around. Therefore, I try to find a trend and bring measured value to the correct level. In the graph, it's shown that cutting forces increase with chip thickness, but higher speed doesn't mean higher force. It's observable in cutting with 0.2 mm chip thickness. At a speed of about 20 meters per second, there is a minimum of force required for wood cuts. It's supposed to be related to the speed of pre-splitting. With decreasing chip thickness is getting substantial friction force. Then the force variation is much smaller at all velocities when cutting a chip thickness of 0.05 millimeters. Below the speed, a crack is formed in front of the knife. At higher speeds, the knife is faster than crack propagation and no pre-splitting occurs. This phenomenon only occurs if we cut wood parallel to its fibers. All of these results we were able to observe thanks to this novel experimental device and our awesome team. Thank you for your attention.